Greetings. In this part we will learn about another variant of the scheduling problem. So it's again scheduling. This time we will learn about the so-called time model. So far we are considering the list model, in which we just had to schedule all the jobs according to the order of their arrival, and then and only then we started the machines and waited for the rest of them to finish. But in this time, in the time model, here we still have, say, m machines, say at least one, that is 2 machines, and with the same processing speed, so it's not different in this time. It's similar to the basic model of the scheduling problem, but each job also has a processing cost, usually denoted pi, so it's the non-negative real value, and an arrival time or timestamp. So arrival time ti. Now, so the sigma I is always just a pair pi ti. Usually I will, in the examples, I will use the first coordinate for denoting the cost and the second coordinate for denoting the time. And the jobs arrive in the order of their arrival time, of course. So the jobs arrive so that, say, the first request comes earlier or at the very same time than the second and the third, and so on. Blah, blah, blah. Usually n is the size or length of the input, which we do not know in advance in this model, not in this model as well. So the jobs arrive in a non-decreasing ordering according to their timestamps or arrival times, and we have to schedule each job to a machine again. So we have to schedule sigma I to some of the machines, to exactly one of the machines. In a time, so it will, a time slot, say from ti, okay, let it close interval. So it's from ti prime to ti prime plus pi. So basically we have to assign some interval of time having length pi on one of the machines, so that the scheduling, so we will just ti is the lower bounds for ti prime, which means simply that we cannot schedule a job to a time slot before it arrives. So basically this says that we do not know the jobs in advance, and this slot, of course, has to be disjoint. So in one machine, at any time instant, at any given instant of time, there can be only one job at most under process. So disjoint or from what other job from the others. And also, this is an online problem, so also to determine also at ti prime, we only have knowledge of those jobs which arrived before ti prime or at ti prime. So of the jobs that arrive no later than the prime. Okay, so in any time instant, if we make a decision, we can only use an information which is already available. Now let's see, and again, of course, and again, so we have to minimize the make span, which is again the time point when the last job gets processed, which is just the maximum, value. Okay, so which is just the maximum value of these bi plus ti primes. Yeah, right. So this is just the time point when the last job got processed. Now let's see an example. So an example, if we have two machines, only two of those machines, and my input sequence is say 2020, and that's all. Then an optimal schedule would be just so if I already have two machines, I'm just putting both jobs instantly to the machine. So at time point 0, I'm just putting the job of size 2 to the machine, and at time point 0 as well, I'm putting the other job to the second machine. And in this case, this scheduling has it's an optimal cost of 2. But things change if say if there is another job like 3.1, which means that at this time point, at this point of time, a third job arrives and we cannot schedule this guy before both machines get idle, so I'm only able to put this job there at the time point, so beginning at time point 2. This is when the job arrived, but this is when I can schedule it, and in that case this scheduling would have a make span of 5 it's 5. 2 plus 3 is 5. Now for this particular input, it would be a better option to just wait. So okay, I'm scheduling the first 20, but not the second one, and I'm just waiting for some amount of time. And of course a deterministic algorithm can only do that. So if you get two jobs of size 2 at time point 0, then well, you can decide to schedule them say after some time has passed. But so for example, if it just waits, then I will get this 3.1 job at time point 1, and now I have two unprocessed jobs. And in this case, I can make the decision of scheduling the job of cost 3, which just arrived, there, and I'm just waiting here, and since no one else arrived, I'm just scheduling the other 20 there, right? So if I just waited and I keep one machine idle, because there might be a long job, a large job arriving just in a couple of seconds, why not? And I will just use the second machine for this job, then this will produce for this particular input the optimal schedule of 4. So here it pays off to wait. But of course you cannot wait too much, because if you wait too much, then for this first segment of the input, the very same algorithm would produce, well, in the best possible scenario, you will produce an output of 3, because you already waited one amount of time. So, and if you see that no one arrived till this time point, then you can schedule this second job, but then you will spend a make span of 3 instead of the optimal make span of 2. So this is kind of a decision when to wait and how, and what should be the amount, the exact amount of time to be spent on waiting. And the thing is, we cannot really do well better than, I would say it will be 4 over 3, because, well, we will make a lower bound. So a lower bound for the best possible deterministic online algorithm So since we have here a lower bound, which means that no algorithm can be better than blah blah blah, we usually create bad enough inputs, and this is again the same situation is shown again by means of a bad input. And again, similarly as before, I will give you two inputs, one being the prefix of the other input, and an algorithm will behave badly either on the first or on the second input. So a bad input sounds exactly this, guys. So it starts with 2 0 and 2 0. What I'm doing here is just 2 0 as an input, so I shouldn't draw boxes, right? So the first input will be 2 0, 2 0, 2 0, and so on. A quite large number of 2 0 jobs arrive at the very first instant of time, so at time point 0. And okay, so how many jobs we have? M jobs. Oh, yeah, that's fine. And now for this part, the optimum is the optimum for the first input is just 2, of course. Now the thing is, if I'm just throwing in these jobs, then deterministic algorithm can schedule, well, some of them. Okay, so let t, which is at least 0, denote the time point, so the time when the last of these jobs gets scheduled by a deterministic online algorithm A. Okay, so for example, in the previous cases, here I'm just switching colors. So here, for example, the T will be 0 because both of the jobs get scheduled instantly. Here the T is 2 because this is the second job, right? So this is the last one to be scheduled and it starts at time point 2, and here T is 1. Each of these arrangements were produced by some different possibly online deterministic algorithm. So here T is something which is just a time point. Now, if T is at least 2, in one of the examples previously, the T was exactly 2, and then since each of these jobs have a size of 2, this will mean that T plus Pi is at least 4. Since the optimum is 2, this means that the algorithm's cost for this particular input divided by the optimum cost is, well, 2, which means that the competitive ratio of such algorithms is at least 2, so they are not that great. Now, otherwise, the second case is that if T is smaller than 2. Now, this means that each machine is working at the time point of 2, so since the jobs cannot overlap and the jobs have a size of 2, since the jobs can't overlap, this means that all the machines are working. All the machines are working at time point T. So I'm just drawing this here. So for example, it's possible that one of the jobs get scheduled here and the other job is also scheduled here, and then one of these jobs gets scheduled there, and at this very same amount of time this job gets scheduled there, and so on. But if this T is smaller than 2, this T here, this means that the last job, okay, so this is also having a size of 2, so since T is smaller than 2, this means that each machine is processing exactly one job at time point 2. Now here the cost of the algorithm is 2 plus T, right? Because this is the last job and we will spending 2 months of time processing this job. So the cost of 2 times 2 plus T, and the optimal cost would be, of course, 2 for this particular input, which means that 2 plus T divided by 2 is a lower bound for the competitive ratio of the algorithm. And now, as I promised, there will be 2 inputs. This sigma 1 is the prefix of the sigma 2, which is just tailored to the algorithm A, and this will contain a job of say 4 minus T. I can throw in here say a minus epsilon or whatever, so it arrives just before or just after this for some epsilon small enough, so it's just a small constant. Okay, because so this is just the suffix and we'll get the sigma 2. Now, of course, since all the machines are working at time point t, the algorithm has to wait, and the earliest it can process this particular input, this piece of the input, is this point. So if there is a job which was allocated onto a machine at the beginning, so in the beginning, so it is at time point 0, then the algorithm can schedule this last job for minus t minus epsilon there. Now in that case the cost will be well, it's 2 plus 6 minus t minus epsilon, so it's 6 minus t minus epsilon, and the optimal cost is very similar to the one we've seen previously, because if this job arrives at t plus epsilon and it takes 4 minus t minus epsilon time to get processed, this means that the algorithm's cost is at least 4, because if I start at this point instantly, then and I spend this time, so the sum of these two guys is exactly 4, and L star is actually 4 for this particular input, because similar to the previous case, I just have to put 2 jobs of size 2 to one machine and say process the other jobs in some other machines, but the last machine is idle till t plus epsilon, and it will just process this last job as soon as it arrives. So in this case the cost will be 4, so 4 is possible to do. So the optimal cost is 4. Now this means that the competitive ratio of the algorithm is at least the maximum of 2 plus t half and 6 minus t minus epsilon divided by 4. And again, I just have to take into account all the possible epsilon values, and actually I can make it 0. So to solve this, I'm again just drawing 2 lines because it's easy to understand. And also I know that t is at least 0, of course, because I won't schedule the jobs earlier than 0, and also this is the case when t is at most 2, so I know this, right? So I have this value of t drawn here, right? And then I have this 2 plus t divided by 2, which is 1 plus t half, so the line comes from here, so this is for 2, and plus t half goes there, yeah? So it's 2 plus t divided by 2, and the other thing is 6 minus t divided by 4, so it's basically 3 over 2 minus t over 4, well, minus epsilon over 4, which means that I can draw these things. So 3 half starts here, great, minus t over 4, so at t equals 2, it will, oh, so at t equals 2, it will be 1, yeah, the previous one will be 1, so it will be 2, yeah, sorry for that. So it's there, and for t equals 2, I will get 3 over 2 minus 1 half, so it will become 1. Yeah, but the minus epsilon over 4, which means that if I'm just ranging over all the possible values of epsilon, I will just get several lines just below this line. Yeah, right. But nevertheless, the maximum of these lines is here, or I could say supremum if you have knowledge about these operators. So this is the maximum, and again, as usual, I should just compute the minimum possible value for the maximum of the maximum by just solving the equality there, solving it for equality. So it's just 2 plus t divided by 2 equals 6 minus t divided by 4, because if epsilon tends to 0, then this is what I'll get. And then I'm just multiplied by 4, so it's 4 plus 2t equals 6 minus 7t, and I'm just adding t here and subtracting 4, so t is 2 over 3, in which case the competitive ratio will be, so the ratio is at least 2 plus 2 over 3 divided by 2, which is at least 4 over 3. So this means that you cannot, it's a lower bound, is a lower bound for the competitive ratio. Yeah, that's great. Now, okay, so now we know that there is no deterministic algorithm for this variant of the problem having a competitive ratio strictly smaller than 4 over 3. But I will show you two possible algorithms which are constant competitive for the problem. So two possible algorithms. Well, I will show you three possible algorithms for the problem. The so-called INTV algorithm, which is probably coming from intervals, and the other is the online LPT. Now, I will start by describing the INTV algorithm. So the algorithm works in phases again. So the algorithm waits till all the machines are idle. So none of the machines are making actual work. So till all the machines are idle, and there is at least one job which is not processed yet, and there is a job which is available, so which is not scheduled yet. Then, if this point in time happens, it will just schedule all the jobs that are available at that time point. Then it schedules all the jobs. All the available jobs in an optimal way. Now this part is just making this algorithm a bit slow to schedule. So it should be upgraded, but it will schedule all the available jobs in an optimal way and just waits till they finish. Okay, let's see an example for this particular algorithm. So an example where I have 3 machines and I will have an input sequence of say 1, 0. So there is a job of size 1 in the very beginning, actually 2 of them, and then there is a job of size 2, and then there is a job of size 3, and then at 1 o'clock, 1 a.m., 1 p.m., whatever. So after 1 unit of time, a job will arrive of size 2, and then after 1 more time, a job of size 2 will arrive, and then a job of size 3 will arrive at 2. Okay, and then at 3 a job of size 1 will arrive, and then at 4 a job of size 2 will arrive, and finally a unit size job will arrive at 5. Okay, now of course these values are integers just for us to be able to compute with them, so make computations using them, but these could be any real values actually. Yeah, so now the interval algorithm, so the INTV algorithm, so I have 3 machines. First it will wait till all the machines are idle, none of them are making any work. Yeah, that's true at time point 0, and there is at least 1 available job. Yeah, sure, we have 4 available jobs right here, right now, which means that there at this point the algorithm will schedule these jobs. Well, in the list, according to the list model actually, because here we don't have to wait or anything, so it's just say 3 here, why not? So 3, 0, why not? It's just 2, 0, and it's just 1, 0, and it's just 1, 0. Now of course you cannot do better, so if you just schedule all the jobs in an optimal way, then because of this 3 you have to spend at least 3 amounts of time. So this is an optimal arrangement, optimal schedule, and then the algorithm just waits. For example, here at time minute 2 we already have 3 jobs available, but we are just waiting because on the first track, on the first machine, there is still some work to do. But at this time point, okay, at this time point all the machines became idle, and I again have 1, 2, 3, 4 available jobs, because these are the guys that arrived before 3 and they are unprocessed. Now I'm just trying to schedule them in an optimal way, but again I have a 3 here, so I have to process this guy 3, 2, and if I just process this guy, and remember I have to use gaps because the algorithm waited till 3 p.m. so it's just 1, 3 here, but from this time point on, this schedule of the unprocessed jobs is optimal. And then I'm going waiting. Okay, great. And I have to wait till 6 because that's the time point when all the machines become idle, and then I will have 2 more jobs. 1 which was already available at 4, and 1 which was available since 5, and then I'm just waiting, and this is the end of the input. So for example, on this particular input, this is how the INTV algorithm works. Usually if you just load the machines in a decreasing way, so the first machine gets the most load, the second machine gets the second most load, and so on in your optimal configuration, then you will end up with a stair-like sequence like this. So you just have here some stair and some gaps, and here you again have some stair, some gaps, and there you also have some stair. That's also it's so if an algorithm produces such schedule, then it is most probably a variant of the interval algorithm. And there is another algorithm. Another algorithm is called the online LPT. Now I just described this guy there. So the online LPT is different. LPT stands for longest processing time. Longest processing time. So this algorithm also waits, but it doesn't wait until all the machines are idle. It just waits till at least one of the machines becomes idle. So it waits till there is at least one. Idle machine. And at least one job which is not scheduled yet. And then the longest processing time means that it will schedule the longest, the largest job. Onto an idle machine. So it's onto the first, if there are more idle machines, onto the first idle machine. And basically that's all what the online LPT algorithm does. So let's just run this algorithm here. So basically we have 3 machines, and in time point 0 I already have 3 machines and I already have 4 jobs. Okay, so the online LPT algorithm will schedule at least one job. So in particular, so this will be this job to be scheduled because this is the largest job at this point. So it will just schedule this 30 there. But again, there is at least one idle machine, and so we just schedule the currently largest unprocessed job, which has a size 2, and then we just schedule this job 10. One of the largest unscheduled jobs to the only idle machine. But that's all what the algorithm makes now, and now it just waits. The interval algorithm also scheduled this last 10 algorithm just at this time point. The online algorithm doesn't do this, it just waits. And it waits till time point 1. Now at this time point, this machine, the third machine, becomes idle, but now we have 2 unprocessed jobs, the 2-1 and the 1-0. And because the 2-1 job is larger, the algorithm will schedule the 2-1 here, right? So the larger job gets scheduled to the idle machine, and the 1-0 is still not processed. Now all the machines are working, so it's just waiting till time point 2 when this machine 2 will become idle. But at time point 2 there are already 2 more jobs that have arrived, so we now have 3 unprocessed jobs, the 1-0, the 2-2 and the 3-2. And amongst of these, the 3 to which is the largest, so that's what gets scheduled. 3, 2. Okay. And now the algorithm waits because there are no more idle machines. It will wait till time point 3, at which point this job becomes available as well. But now we have one largest job, which is the 2, 2, and the machine, so the first machine is also idle, that's fine. But we also have another job, 2 of them, the 1, 0 and the 1, 3, and we have one idle machine. So at this time point, I will just schedule one of these unit cost jobs, and to satisfy some fairness feeling or whatever, I'm just scheduling here in the case of ties the job which is here for a longer period of time. So when the algorithm just waits till time point 4, in which at which time the job of size 2 will arrive, and at this point this will be the larger amongst the 2 jobs. So the algorithm will schedule this guy there, 2, 4. Yeah, that's great. And then we are just waiting till 5, and at 5 this last job also arrives, but we have 2 machines, 2 idle machines, 1, 3, and it's fine, and another machine is 1, 5, and it's 5. And we are done. So if we use the online LPT algorithm for scheduling, then in this case we will get a better schedule. And of course this is optimal because again it's easy to see that the L star, the optimal value, is at least as large as the maximum value of the PI plus TI values, right? So it's just, which is 6 in this case, because a job of size 2 arrives at 4. So even if I immediately schedule this job, I can finish at 6 the earliest, yeah? And this bound is also produced by the other job of 1, 5. And of course it's also true that the optimal value is at least the sum of all the processing times divided by n, because this is a schedule. So it's and in this case I'm not sure what it is, but it's 6, of course. Yeah, it's again 6, and this is again 6. But this is only a general lower bound which holds for all possible inputs. Now in this case the online LPT algorithm was better, and in general online LPT is 3/2 competitive and the interval algorithm is 2 competitive. So we can say that in the general case that online LPT is simpler to implement, simpler to understand, and also better from this competitive analysis point of view. But we will prove this, that the INTV algorithm is too competitive. Now let's just have a break right now, because the video is taking a bit long, but in the next part I will prove that the INTV algorithm is too competitive, and that will conclude the whole scheduling chapter of the course. Till then, bye bye.